Right. Assalamualaikum. Good morning. Um, let's resume our lecture. And today's lecture will be the last lecture for this course. So we have reached the last LU. Right. Okay. I suppose you guys have covered all those recorded lecture for the past few weeks. Yeah, I'm sorry I didn't because of the tempo bertenang, and then yeah, I think because of I don't want to burden you with the live lecture, so I have the recorded lecture for the past few LUs. Hope you guys have covered it, right? And engaged with the activities that I have prepared on ELIP. Okay, so basically, we have we have covered 7 LUs, yeah, altogether. And the LUs are divided into upstream, most of the LUs, and 1 LU on downstream processing. So by right, you should know that bioprocess, the field of bioprocess consists of that 2 subfields, upstream and downstream processing. Okay, that's the 2 main field in bioprocess technology. But under upstream processing, there are actually many branches, and one of them is fermentation. Under downstream processing, there are also many stages, many areas, yeah. And we just like the LU just cover the brief picture about downstream processing, but basically what you should know about downstream processing is a stage after the production. Fermentation is the production stage. So after the fermentation, after the production, you would have the culture growth, basically. And what you have to do with that culture growth, you have to do several procedure under the downstream processing in order to separate and purify the product of interest. So because you know that after the production, after the fermentation, apart from your product of interest, which is the main product, there are other byproducts that are also produced by the cells. Yeah, for example, some metabolites, but those metabolites might not be your interest. You want to actually just get your end product. So how to get rid of those unwanted metabolites? You have to do certain procedure under the downstream processing. So that's the importance of downstream processing. Upstream is important because of the production. So without production, there is no product. So in order to produce the product, you have to grow the microbes. So that's fermentation is all about. And there are many aspects of fermentation that you should know. Platforms of fermentation, the food, which is the media, and then what are the types of fermentation? They are solid state, liquid state fermentation. What are the things that we should do during the fermentation? We should sample, we should monitor the growth, the cell growth, because without the cell growth, there would be no products. And then we also have to monitor the substrate consumption, because substrate consumption is associated with the cell growth. So if the cell grow very well, it means that it consumes the substrate or the media. So the substrate should be reducing, isn't it? And then also we should also monitor the production of the product of interest. So the product, let's say whatever the products of interest, it should be increasing. That is the ideal case scenario. Yeah? So if let's say the product is not increasing, there must be something wrong with the fermentation. The production doesn't happen successfully. Yeah? So all those things you should monitor during the fermentation. So yeah, so that's covered in the fermentation topics, upstream topics, and then you have covered downstream processing. What you have covered in downstream processing is just very superficial, yeah, very basic. Not to say we just cover, like, you know, there are centrifugation, filtration, purification, but for you to know that that field actually it consists of many specific fields. So like, for example, centrifugation, there are so many things to be studied actually in centrifugation. In purification, in HPLC, in chromatography, for example, in filtration. Each of that is actually a huge field, but we can't cover in detail, but it's enough for you at this point to know that downstream processing consists of those processes. Okay. All right. So what I have prepared last week. Oh yeah, I have prepared the some activities for LU6 as well. And then LU7, you guys have to read and engage with the pop quiz, right? Okay, make sure you do that. Yeah, that would be a good revision for you for the final. Yeah. Okay. So today's topic, we're going to cover scale up of fermentation process. Okay, so we go back to a little bit to the fermentation. Yeah? So LU1 to LU6, we talk about fermentation basically. And then LU7 is about downstream processing. And now we go back to fermentation. Okay, the topic is on the scale up. Okay, scale up of fermentation process. So this is the outline of today's lecture. We're going to cover what is the background of scale up of fermentation, objectives of scaling up, when do we need to do scaling up studies, what are the stages in scaling up studies, the changes in the operation of fermenters during scale up, methods in scale up fermentation, and finally is the case reviews. Okay, so that's what we're going to cover today. Okay, first thing first. So some introduction about scale up. Okay, so the term scale up, that is actually is a generic term. Generic term. Scale up is, but now we are focusing on scale up of fermentation. But when we talk about scale up, it could be anything. It relates to any process, anything that involve or include the action of increasing something in size, amount, or production. Okay, that is the general definition of scale up. Okay, so it's a generic concept, meaning to say that it's not only limited to fermentation, it can be applied in downstream processing units such as centrifugation, filtration. There is a scale up of centrifugation. There is a scale up of filtration. There is a scale up of chromatography, and yeah, so it can be applied in many applications. But in this topic, we're going to cover scale up of fermentation. So when we talk about fermentation, we know that it's a process of growing the microbes to produce products, right? And involves microorganisms. So when we relate scale up and fermentation, it means that it involves the action of increasing the size of the fermentation scale. Okay, so what does it mean? So for example, if let's say we have fermentation, you know that fermentation can be conducted in various platforms. The simplest traditional platform is shake flask, isn't it? So and shake flask is regarded as a lab scale and a small scale, because it's normally it's up to either one is up to 1 liter, but if let's say you want to have more than that, you have to use different platform. But shake flask is one of the platforms in the kit. So having said that, shake flask is a small scale. So if let's say we want to increase the fermentation in the shake flask to a larger scale, for example, in fermenter. because we want to get more products, right? So the action of increasing the size of the fermentation, that is scale up. Okay, and we know that fermenter, there are various sizes of fermenters or bioreactors. Yeah? So some bioreactors are small, some bioreactors are big. Okay, depending on the needs and the purpose of the fermentation. Okay, for example, if let's say we have 1 liter fermenter, 1 liter fermenter, and then we want to scale up to, let's say, 100 liter fermenter. Okay, this is the schematic diagram of fermenter. Okay, so when I draw this tank, it refers to fermenter. So if let's say we want to increase, let's say we have conducted fermentation in 1 liter fermenter, and then we found out that the result is good, and then we want to get more products. Let's say we produce bioethanol and we want to get more bioethanol, so we have to use larger fermenter, like 100 liter fermenter. So the action of increasing the size is called scale up of the fermentation process. Okay, so when we increase the scale, yeah, so what we expect when we increase this, the size of the fermentation, let's say from 1 liter to 100 liter fermenter. So we expect that the performance is to be consistent, is to be the same. Yeah? Let's say you got like high bioethanol production in 1 liter. Let's say the ideal, maybe the yield is about 0.6, and you are happy with that yield, gram per gram. And let's say you are happy with that yield and you feel that that is the best yield that you feel could be profitable. So if you want to increase the production to larger scale, you should expect that your objective is to get the same yield or the same productivity, example 0.6 gram per gram of yield. So the objective is to get the same productivity and quality. It's not to get higher quality. That is not really correct, because the purpose of scale up is to get the same productivity, the same quality as what developed at small scale. Okay, so that's fair enough. So what else? Fermentation is usually the costliest and complex unit operation. Okay, so why there is why actually scale up is one area of study in bioprocess. So we don't just increase the scale of the fermentation just like that. We use large bioreactor and then we put the microbes and we run it. No, so you have to know what are the strategies, the methods, the right methods for you to increase the size of fermentation. So there are things that you need to study like that. So it's not just a simple process. So the reason why we need to study, why we need to have a proper plan when we want to scale up is because fermentation, fermentation is a production process. It's an expensive process. It's a complex process. It's a complex operation. You have covered previous topics on fermentation. It involves lots of things. The types of media, even we talk about types of media, there are so many types of media. And if let's say you change from one type to another type, you need to do like a thorough study. You need to know what's the effect on these and these. And even if you change one component of the media, it involves the whole thing again to be studied. Okay, so having said that, fermentation is not an easy process. And it's not just about the media. You have to also consider, for example, the effect of other culture conditions like the pH, the temperature. If it is an aerobic fermentation, you have to know like how much oxygen is good for the fermentation. Okay? Sometimes they might not need that really much oxygen. So you have to know that through study, through research. So in order to establish, let's say you want to establish one new fermentation process, it takes sometimes actually to develop the effective strategy. So strategy, when I say strategy, it means it involves lots of things. The media, and even before the fermentation, the microorganism it also needs like studies on that. For example, if let's say you want to isolate, the first thing before the fermentation is you have to know what kind of microorganism that is suitable for the whatever the production, let's say the lactic acid production. Let's say you want to produce lactic acid. So you have to know what kind of microbes that can produce lactic acid. And how you want to know, you have to do isolation and screening studies. So that is the step before the fermentation. So in general, the steps, the fermentation process or the upstream process is a huge thing. It's a complex process. So when it is said as a complex process, so when we want to increase the production, it involves lots of costs. So if let's say we just do without proper planning, like 100-liter fermentation, let's say you increase the fermentation to 100 liter without proper planning. So it will involve lots of cost, energy, and also manpower. So scale up of, proper strategies or methods to scale up the fermentation is very important, and it involves a thorough planning. So that's why there is a scale up studies is something that needs to be taken into consideration in the upstream. Scale up serves to minimize the risk of a large capital investment in the full-scale manufacturing plant by further validating the process, the supply chain, and market demand. So if let's say we have a proper plan, we know, we have a proper strategy that that has been approved or validated by previous works. There are rules of thumb that we will cover after this of scale up. So if we follow that, so it will reduce the risk of the waste, the risk of the unsuccessful operation large scale. So because when we talk about products, when we want to produce like fermentation products, they are produced for the sake of mankind. For example, bioethanol. When we study about bioethanol, the long run aim is to ensure that the bioethanol can be eventually benefited by people, to be used as biofuel, for example. Okay, for example, like if let's say you study about certain vaccine, we want at the end the vaccine to be benefited by wider people, isn't it? It's not just by you. So that is the purpose of any bioproduction in the first place. But in order to enable that, you have to know like certain procedure to increase the production so that it will fulfill our objective, the objective of the bioproduction. All right, so that is basically some backgrounds of scale up. Okay. So the second part is why we do the scale up. Okay. The objective of scale up, why we want to increase the fermentation scale, is because we want to produce more products. We want to get more products, because when we study in the lab, right, we carry out fermentation in the lab using, for example, 1 liter fermenter. That amount is not enough if let's say we want to market it. There are things after that. It's not just ended in the lab. So for certain products that has commercial value, we know that the enzyme is, for example, certain enzymes, they can be useful for treating wastewater, for example. So we cannot rely on the lab to produce it at larger scale. So in order to scale up it, we have to transfer the production from the lab to pilot scale and to the industrial scale. Okay, so that process is called scale up. So that's one of the objectives, is to ensure that the fermentation is technically and economically viable at larger scale. And then to produce products of commercial value and to derive profit from the process. So I've mentioned about it as well. So of course, when you market your products, you get the profit from it. Yeah? So so without having a large production, you cannot market it, you cannot get the profit. So that's one of the objectives. And then to increase the production capacity of a unit, thus lowers the investment, variable and production costs. So if let's say you produce something in large scale, it would actually reduce the cost per unit. So that's the reason why if let's say you buy something in bulk, you would get like cheaper price, right? Let's say you buy anything in the market. Let's say you buy 1 unit and compared to let's say 1,000 units, the cost of each unit, if let's say you buy in bulk, would be cheaper if let's say you buy in bulk, isn't it? Rather than if you buy one, because whenever you, let's say a factory produce like 1,000, they have invested actually the same amount of energy, manpower maybe, and then electricity to produce that compared to let's say, I mean the same amount of all those things to produce big amount of products and then compared to one amount of products. So those costs will be shared by that large amount of things. So that's why in terms of per unit, the cost will be reduced. So that's the reason why it is recommended to produce things in bulk. Yeah? So in order to produce that, we need to know what's the methods of scaling up. Okay. So when do we need to do scaling up studies? So basically, when we have any new fermentation process, and we know that the fermentation process produce a product that has a commercial values, that is when we need to scale up. Okay. So basically, any factories, if let's say, even though they have established certain production, but let's say they come across like a certain new things in the production, let's say new media, new bacteria, or new whatever the things that is introduced in that fermentation process, they have to actually start from scratch. They have to learn how to do the fermentation at small scale and then how to increase the scale in stages from lab scale to pilot scale and to industrial scale. So basically, scaling up is needed for any new fermentation process, for any change in the medium, strains of bacteria, fungi used, and if let's say it involves any new fermenter, any new fermenter, let's say even though like for example for an established production, they have used certain old bioreactors, and let's say they want to use the new fermenters, they have to study from scratch again how the production can be translated from a small scale reactor to a larger scale new reactor. Okay. So what are the stages in scaling up studies? Okay, scaling up in fermentation, it involves a few stages. So these are the stages. The first one is the laboratory, pilot, and then industrial. So these are actually the scales that a product has to go through before it is marketed, before it reach the consumers. Okay, so anything, it would start with the lab scale, with the lab studies. So this is actually lab. Okay, so lab. So when you study, like for example, when you start your FYP, that is actually the starting point of any new research. Yeah, and maybe like 10 years or 20 years from now, the product that you produce during your FYP could reach the industrial scale. So it takes time because the process of studying it is not easy. So, but anything, it will start with the lab scale, with small scale. Lab scale is normally associated with small scale. So the traditional platform that we normally use are shake flasks, okay? But there are also new trends of using advanced platform that replace shake flasks. such as mini bioreactors and microbioreactors. We have covered this in LU6. Yeah? So these are the new technology, but shake flasks are still used in these days. Yeah? So this is the new technology because they have new features that are better than the shake flask. But they are still considered under lab scale. And then after shake flask, after the mini bioreactor or microbioreactors, they are also fermenter, but the size is not that really big. So they are called bench scale or lab scale fermenters. So normally this one is up to like 10 liter, 10 liter. So for lab scale, you should know that there are two stages actually. The shake flask, mini bioreactor, microbioreactor. This one is normally less than 1 liter, the scale or the working volume. For the bench scale fermenters is normally they are 1 liter fermenter, so and up to 10 liter. But this definition could vary from one laboratory to another. So this is just the basic range, I can say. Okay. And then after the lab scale, there is a scale called pilot scale. Pilot scale. So what is this pilot scale? Pilot scale is the intermediate scale between the lab and the industry. So it's a transition intermediate scale. So it means that it sits in the middle. So the scale is much bigger. It could be more than 100 liter. Okay, 100 liter. So it means that once we have established whatever the fermentation production in the lab scale, and then before we want to transfer it to the industrial scale, so it should be transferred to pilot scale first. So it's not just that, I mean, it's not to say that it's not too sudden, if let's say from lab to the industry. So if so this pilot scale behave as the intermediate scale. So whatever the errors or the things that can be improved, we can still improve it at the pilot scale. So the reason is because it will reduce the cost to minimize the failure and also the waste and also the cost if let's say something happened. Yeah? So that is pilot scale. And then after the pilot scale, after let's say the production is successful at the pilot scale, and that is when it is transferred to the industrial scale. So the process from lab scale to pilot scale, that is scale up. That is, I can say that's the first stage. Yeah? Whatever it involves the transition of the scale, that is scale up. And then from the pilot scale to the industrial scale, that is also scale up. Okay, so that's what you should know. So industrial scale is the final scale. So that is where the products are produced in large amount, in maximum capacity. And after that, it will be marketed to the consumers, whatever the products. So before any steps are taken to produce any fermentation products at industrial scale, preliminary studies must be performed at lab and pilot scale first in order to ensure whether the intended product technically viable, yeah, the process or the new products are economically viable, or whether the production process is feasible. Okay, so that's the importance of the studies conducted at lab scale and the pilot scale. Okay, so those are the stages in scaling up studies. So let's have a look in detail for each of the stages here. The first one is the lab or bench scale. So as I mentioned, the platforms that are normally used are small scale platforms, shake flasks, micro bioreactors, mini bioreactors. So the studies that are conducted at this stage is basically preliminary. So what is meant by preliminary? They are the initial stage of studies. Yeah. So we want to know, for example, the best microorganism, but we don't want to produce. I mean, we don't want to have big production yet. So that's why we conduct the fermentation in small scale using shake flasks or using mini bioreactor or microbioreactors. So the types of studies, they are preliminary, and they can be divided into screening studies, optimization studies. Okay, so you should get used to these terms. Screening studies means you want to screen, you want to identify, for example, producing microbes. Let's say you're focusing on production of enzymes, let's say amylase. So you want to know what microbes that are capable of producing amylase. So the process of selecting it, the process of identifying it, that is called screening. So maybe you isolate samples from soil, samples from water. And then you screen, you maybe like you culture it in the media, in the lab, and then see the growth. And you do like certain analysis in order to check whether the microbe produce your product of interest. Okay. So that kind of study is called screening. And screening is conducted at lab scale, and it involves this kind of small scale platforms. And then another type of study is optimization. Optimization means that once you have screening comes up before the optimization. You have to screen first the best microbe, and only then you proceed with the optimization. Optimization means once you have the microbe, you know this microbe, let's say, produce amylase. And then what you have to do is you have to grow it well, isn't it? So in order to grow it well, you have to know what is the best culture conditions. Culture conditions means what are the best conditions that the microbes can grow. For example, the temperature, what's the temperature? So it must have its own favorite temperature, isn't it? So some microbes can grow at 30 degrees Celsius. So some microbes can grow at 50 degrees Celsius. So you should know that. And then pH. What is the best pH for the microbe to produce the product of interest? And then the medium concentration. So medium is a general term for the substrate, and it could be it could be a formulation consisting of a few components. You study about medium formulation, right, in the second element. So in order to create a recipe for the microbes, you should know what are the components, and how to know the components is through studies. You have to check one by one, and it's not just about checking the types of the component, but also you have to check the concentration. How much? Let's say glucose. Let's say you know that E. coli can eat glucose, can consume glucose, but you should also know how much glucose that you should supply, whether it's 10 gram per liter, 20 gram per liter, 30, and so on. Okay, because there are certain amount of media that the microbes can eat. So after that, they cannot eat anymore, and maybe they are not happy. They don't produce the product of interest. And in a worst case scenario, they would, those high substrate concentration can become toxic to the culture. Okay? So those things you should study. So all those things are covered under optimization. So optimization studies cover all this stuff, all these aspects. And what you should observe during this, you should observe the cell growth, you should observe the substrate consumption, you should observe the product yield. Okay. So these kind of studies are conducted using shake plus yield. Not all laboratories have micro or mini bioreactors because the cost of these platforms are expensive. But most laboratories would have shake plus. So normally, by default, the studies would be conducted using shake plus. Okay. Conventional platform in shake plus since 20 years ago, the trend is gradually moving. Yeah. So, but you should also know the existence of micro bioreactors and mini bioreactors. So the mini and micro bioreactors, they are usually in high throughput platform. High throughput means they exist in many units and they are embedded together. So for example, like micro 24, this is for example here, there are 24 wells. Wells are like tubes. So you can carry out 24 fermentations at the same time. So it means that it saves you a lot, like you can do more experiments. Let's say 24 fermentations. You can carry out, for example, let's say you want to study the effects of pH, pH let's say you want to study about the glucose. So you can have like many parameters at the same time. So that's the benefits of microbioreactors, high throughput microbioreactors. Okay. So that is the lab scale for the, what are the things involved in the lab scale. So the second part of the lab scale is the bench scale fermenter. So let's say once you have established, once you know already what's the best microbe, you know already what's the best pH, what's the best temperature, what's the best medium, then means that you have established the fermentation, optimal fermentation at a small scale, at shake flask or mini bioreactor or microbioreactors, then you have to transfer it to bench scale fermenters. Means that within the lab scale, you also need to scale up. So from, let's say, from the mini microbioreactor to higher, to larger scale, to larger bench scale fermenters. So that is also a scale up process. Yeah? So the reason is because, so once you have established the optimal conditions at lab scale, at shake flask or at mini bioreactor scale, you want to know, let's say this one is like maybe 5 milliliter, so which is very small for microbioreactor. So lab scale, you have, let's say, 10 liter fermenter. So you want to know how good it is, how good the fermentation that you have established at 5 milliliter at 10 liter. You know what I mean? So that's the reason why you need to scale up. Okay. So after the optimal conditions of fermentation have been established in shake flask, the fermentation needs to be translated to the lab scale fermenters. Okay, I've mentioned about it. At this stage, more in-depth studies are carried out by observing the effects of increasing the size of fermentation, the method of fermentation from batch to flat batch or continuous, duration and product. So means that you need to observe it still, even though you have established optimal conditions at smaller scale, but you need to know how it varies at 10 liter, for example, at 2 liter, 5 liter, okay? And you also have to observe all this stuff. And apart from like the culture conditions, the type of organisms to be used for the fermentation, another area of study in fermentation is to evaluate the feasibility of whether batch, fat batch, or continuous is suitable for the fermentation. So batch is, it means you have the fermentation, you put all the media, and then you let the fermentations to carry on. So it means that there's nothing going in and out during the fermentation. That is batch. Fat batch is when you have the fermentation, you insert first some media, and then you let the fermentation takes place. So when you say fermentation takes place, you put the microbes, put the inoculum into it, and so the fermentation takes place. And during the fermentation, you insert a certain amount of substrate, or maybe like glucose, glycerol, during the fermentation. So that is fat batch, but you don't withdraw anything from it, okay, during the fermentation. So that is fat batch. So it comes from the word feed. So you feed something during the fermentation. Continuous is when you have the fermentation takes place, you insert something, you take out the product. You insert something, you take out the product. So there is input and output during the process. So that is continuous. So some, normally at industrial scale, continuous is performed, but depending on the types of fermentation as well. But you know that the suitability of this kind of format is to be evaluated during the studies at the lab scale fermenter. Okay, so that's the importance of this stage. Okay, so the data obtained should reconfirm previous experiments. If not, adjustment will have to be made. Yeah, so that's another reason. When you transfer the production, the fermentation from, let's say, from shake flask to the lab scale fermenter, you want to check whether the yield is the same or not. So if there is something wrong, you have to adjust a little bit. Yeah? So it means that you can still adjust at the lab scale. So rather than if, let's say, you transfer it directly to industrial or the pilot scale, it will involve lots of cost and energy. Yeah? These parameters should remain the same during the translation, the type of inoculum, the pH, temperature, and also the medium formulation, because this has been established during the shake flask studies or the mini bioreactor studies. So that is the lab scale. So basically it involves proof of concept study, whether to check whether the production happens or not, whether your product is good or not. So the second step, so once you have established the production at the lab scale, yeah, so you have studied at this the first stage, the shake flask or the mini bioreactor scale, and then you have transferred to the bench scale fermenters, and I mean the result is good, the fermentation performance is good, and only then you proceed with the pilot scale. Yeah. So means that the scale is now increasing. So means if let's say at the bench scale you are using like just 10-liter fermenter, at the pilot scale maybe you are using 100-liter fermenter. So you see the scale is increasing, although it still involves let's say the same type of bioreactor. Yeah. So pilot scale is the second stage in scaling up studies. So it's the intermediate scale between lab scale and industrial scale. Capacity is said to be between 100 and 10,000 liter fermentation. This stage is needed due to changes in the scaling up involving fermentation volume, sterilization method, duration of fermentation, product yield of a substrate. Okay, so whenever you increase the fermentation, because of the volume is increasing and everything is the geometry of the reactor is changed, those kind of things would have an effect on the culture. So that's why we need to check how it behaves in the 100-liter first before we transfer it to the industrial scale. So that's the importance of pilot scale. And also in terms of the sterilization method, okay, because the reactor is bigger. For example, like lab scale fermenter, if let's say you have a 2-liter fermenter, the way how you sterilize it, sterilize means you get rid of the things before the fermentation. Normally it's by autoclaving. You can autoclave the 2-liter fermenter, like 2-liter you can just put in the small autoclave. But if let's say you have a 10-liter fermenter, you cannot autoclave it using the normal autoclave or the small autoclave. So there is a certain way of sterilizing it. Normally it's in situ sterilization, where the steam is connected directly to the fermenter. So the fermenter is static and then the steam is connected to it, and that's how the sterilization takes place. So that is the difference between small fermenter and large fermenter. Okay. And then in terms of duration of fermentation, product yield of a substrate, there would be a change between the fermentations in small scale and large scale fermenter. Okay. So all those things need to be reconfirmed during this pilot scale in order to make sure that the fermentation process is reproducible between the two scales. Pilot scale stage also allows a good opportunity to test new procedures before any huge commitment is needed at commercial or industrial scale. So that is pilot scale, and the final scale is industrial scale. So once everything is good at pilot scale, everything is established at pilot scale, that is when you increase the production to industrial scale. So industrial scale is also known as commercialization or manufacturing scale. So it's normally the factory scale. Yeah? So factory scale. So the fermented volume is more than 5,000 liter. It depends on the industry. So it depends on the scale determined by the industry. So some industry might be very big, some industry might be intermediate. So they have different capacity of the fermenter. The aim of this stage is to produce products that can be commercialized and marketed to consumers. So obviously, because of the scale is big, the ultimate aim is to produce products, to market the products, to get the profit. Yeah? So that's what this stage is all about. So you can see that it starts from the lab scale to the pilot scale and finally to the industrial scale. So that is the last scale before the final product is reach the consumer. Okay, what are the changes in the operation of fermenters during scale up? So even though it involves like maybe like the same type of fermenter, like for example, stirred tank fermenter. Stirred tank fermenter is the one that has the stirrers. So even though it's of the same type of fermenter, but because of the size is not the same, so there are few changes that need to be made during the scale up. Okay. So the first one is the power. Okay, of course, big reactor needs more power than the small reactor, and also it needs certain configuration of this agitator, for example, agitator. So the configuration of agitator in large reactor might be a bit different from that in small reactor. Okay, because of, and also the needs will be also different because in large reactor it needs to stir the things in huge capacity, right? And there are a lot of aspects that need to be taken into consideration. For example, the heat distribution, things like that. And then the size and volume of the fermenter will also affect mixing efficiency of the medium and nutrient distribution, temperature and pH of the control system, number of impellers, and design. Okay, for example, if let's say you have small reactor of course is very easy to control. You can make sure that the mixing is efficient. Let's say at 2 liter, it's not really a big problem. But if you're talking about let's say 100-liter reactor, yeah, so the mixing will be a bit challenging because it's not very straightforward. It's not that really easy to make sure that the contents within this 100-liter reactor will be mixed homogeneously, efficiently. So for example, if let's say you apply 700 RPM in 2-liter fermenter, this speed might not be suitable to be applied in bigger reactor. So it takes a lot of other consideration. Okay, and also in terms of the heat distribution, yeah, whenever the mixing takes place, first there is a heat generated, and how those heat can affect the culture, that is another thing. So there are many things to be considered when you increase the size of the fermentation. Yeah, and the number of impellers. Let's say in 2-liter fermenter, you might need maybe 2 impeller. 2 impeller is enough. But in a larger reactor, because of the height is now increased, right? And the number of fermenter would be also increased. You might need more than 2, maybe 5, 6, depending on the size. Okay, so those things need to be taken into consideration. And then heat transfer, changes in size. Yeah, talked about heat just now. And you also have to know like the heat generated, how it affects the culture inside the fermenter. Okay, whether it affect the product, whether it affect the cell growth or not. If let's say for the small reactor, it's not that really complicated because you can easily control it. If let's say the heat exceeds certain level, then you can easily adjust the mechanism of the heat transfer. But for the large reactor, it takes a lot of other consideration as well. Yeah? So it's not that really straightforward for the large reactor. Okay, so those are the changes in the operation of fermenters during scale up: the power, the amount of power, the size and volume of the fermenter, and also the heat transfer. Okay, methods in scaling up fermentation process. So these are the methods that have been researched or decided by engineers in biochemical engineering. So when we want to scale up, there are certain rule of thumb, there are certain procedure how you want to increase is based on what. So these are the rule of thumbs that have been decided by them. Okay. Yeah, there are certain rules of thumb that are applied to the scale up of fermentation. By applying this rule, one assumes that certain criteria which are optimal on the small scale can also be considered optimal at the larger scale. So what are the parameters? What are the scale up parameters that have been outlined by them? Okay. So there are actually, if we talk about scale up strategy, there are actually various strategy. So it involves like any of this. But how we want to know which strategy is working well, it depends on sometimes trial and error. It depends also on the nature of the fermentation. Let's say whether the fermentation is aerobic or anaerobic. Okay, so it depends on such factors. So let's have a look at these parameters. All of these are the parameter here listed here from 1 to 8. They are called scale-up parameters, and they are used as a basis for the scale-up. So for example, reactor geometry, volumetric oxygen transfer coefficient, or known as KLA. So this one is widely used for scaling up aerobic fermentation. And then power input per unit volume of liquid, volumetric gas flow rate per unit volume of liquid, superficial gas velocity, mixing time, impeller Reynolds number, and specific aeration rate. Okay. So it means that what is the rule of thumb is that to maintain these parameters constant during the scale up. So it means if let's say you choose the strategy of using volumetric oxygen transfer coefficient or KLA, so you have to, I mean, there are certain procedure of carrying out the studies. First, you have to characterize the KLA in small scale reactor, and then you have to characterize the KLA in larger reactor and find the similar value between those, and then you use that as the basis for the scale up, okay, things like that. But the key point here is that to maintain all of these parameters constant during the scale up. Okay, I'll show later in the case review what is meant by that. This part is actually quite is more to engineering part, because in biotech there is also a subfield where it's called biotech engineering or biochemical engineering. So in biotech science, might be it's not that really a focus in biotech science. So don't worry about that. Okay, this is just an introduction. You don't have to worry about how to find mixing time, how to find the Reynolds number. But it's enough for you to know that these are the scale up parameters that are used for scaling up fermentation. Okay. Scale up strategies may adopt any one of the scale up parameters. Okay, so what is meant by any one of the scale up parameters? It means that if let's say we just use KLA, so it's just one of the strategies. It could also use a combination of those parameters. Let's say you want to use a combination of KLA and also specific aeration rate. So that is the strategy. It consisting of that two parameters. Okay, so that is meant by combination of the parameters. And how to know whether it's good on certain fermentation process is based on trial and error. It's based on research. Okay, so there is no one strategy that fits all scale up process. So before the scale up, characterization of the scale up parameters in bioreactors at both scales is needed. This is crucial in determining the constant value of the scale up parameters that needs to be applied for the scale up between the two scales. So what is meant by the characterization here means that if let's say you decide to use KLA, KLA is the volumetric oxygen transfer coefficient, which is a common parameter for scaling up aerobic fermentation. So you have to do like a small study called characterization of the KLA. So it means that you have to understand how the KLA behaves in small reactor and how the KLA behaves in the larger reactor. So there are certain procedure how to determine KLA. Yeah, so that kind of studies are important, are needed before we scale up the fermentation process. So these are examples of the results of KLA characterization. Okay, so examples of the characterization words, right? So you can see KLA, how it changes in, let's say this is micro 24, is a small scale reactor. Is 10 milliliter, and let's say this one is 7.5 liter. So it means that you have to study about KLA, the version of KLA in small reactor and version of KLA in larger reactor, and see how those two profiles compare to each other. Okay, right. So the last part would be the case review. Can I just continue without any break? All right, so let's have a, is it okay, guys? Okay, let's have a look at the last part. Okay, this is just a case review. Like, it's just to show you an example how scale up fermentation scale up is carried out. Yeah? All right, so this case is about the fermentation is about producing transaminase using recombinant Escherichia coli. Okay, and the platforms involved is mini bioreactor, which is micro 24 in this case, and the objective is to scale up from micro 24 from which is a mini bioreactor to a 7.5 liters third tank fermenter. Okay, so you can see in the picture here, this is the micro 24, this is the 7.5 liter reactor. So the reactor is a lab scale reactor. This one is the reactor. Okay. So the working volume in the micro 24 is 6.5 milliliter, because it's a mini scale. Yeah? And then the working volume in this 7.5 liter is 5 liter. So it means that the scale translation, you have 5 liter divided by 6.5 milliliter. 5 liter is 5,000 milliliter, isn't it? 5,000 milliliter. So it's equivalent to 7694. Okay, so that is the scale translation. Okay, so how many fold the size is increased. Okay, so you can see that it's a lot. 769 fold is a huge number actually. So it means that there are changes in the nature of the fermentation. In the nature of the fermentation. All right, so the scale up method here is a combination of constant volumetric oxygen transfer coefficient, which is KLA, and specific aeration rate. Okay, that is the methods chosen. Yeah, so it's a combination method. The reason why KLA is chosen is because this fermentation is an aerobic fermentation. Aerobic means it requires oxygen. So KLA is a parameter that describes the oxygen transfer. Okay. All right. So some background of this fermentation process. Optimal production of transaminase by E. coli was initially established in micro 24. So the fermentation was further scaled up to lab scale fermenter in order to ensure that transaminase can be produced in larger amount, but still at lab scale. Yeah? So here you can see that 6.5 milliliter is each of this is very little actually. So we want to know how much the production at 5 liter. 5 liter. So that is some backgrounds of the fermentation process. So how to carry out this work? Yeah? So I think this is actually my work during my PhD studies. So this is what I did, how I carry out the scale up of fermentation, um, of this fermentation. So the first step is to characterize KLA. I didn't go into the fermentation yet. Right? So this is meant by the characterization studies. So I have to understand how the KLA varies in micro 24 and in this 7.5 liter reactor. So there are certain procedures how to characterize it, how to determine it, and how to get the profiles of KLA in both platforms. But that is the first step to be done. Okay, and then once I have characterized the two profiles, the KLA profiles in both platforms, the second step is to find the overlap match KLA value between both platforms. So actually, the first step here, the results are this one. This is the results of the characterization. This is what I got. I know that the KLA varies like this, up to certain agitation speed, and this is in micro 24. All right, so once I have characterized it, the process is called, the study is called characterization. So once I have characterized the KLA, I have to find what's the match KLA value. So this is, if I combine the two profiles just now, so this is the KLA profile in stirred tank fermenter, right? And then I compare it with the KLA profile in the micro 24. And I have to find the overlap KLA values, which is the value that exists in both platforms. So the values is this one. This is what I got. Okay. So here is 66 per hour. That's the value of the KLA. So what I do next with this value, because KLA, this one is additional information that you have to know. The KLA, it depends on agitation speed and also air flow rate. So these are the two factors that influence the KLA. Okay. So once I have one constant value of KLA in both platforms, I have to determine the speed. The purpose of knowing the constant value is to determine the speed, actually, the speed for both vectors. Okay. Right. Yeah. So here you can see that the KLA is maintained at the same value. So these are some other information about the two reactors. There is a certain formula how to determine the speed from the KLA values. Okay. So this value I obtain from that formula. Okay. So knowing that I want to set KLA at 66 per hour, then the speed that I have to apply in small scale and in larger scale is this one, 800 RPM, 298 RPM in the larger scale. So you can see that the speed is not the same because of the nature of the reactor is not the same. So so based on these operating conditions, I run the fermentation. Yeah, I run the fermentation in the two platforms and see how and observe the performance. Yeah, observe the performance. So these are the results. Run the fermentations, and the fourth step is to run the fermentations in both type of reactors and see the performance. And the fifth step is to analyze the fermentation performance. So what I meant by fermentation performance is the cell growth, the substrate consumption, and the product formation. Okay, you don't have to worry about this complicated graph, but that is the thing. We want to know how much is the cell growth, how much is the substrate consumption, and how much is the product formation in both reactors. Are they the same? Are they similar? Are they reducing or not? Or are they increasing or not? So my target is to achieve similar performance in both reactors. So similar performance means that the performance is consistent. The performance is reproducible at larger scale. Okay. So that's the reason why I have to analyze the fermentation performance. So these are examples of the results that I got in Micro 24, right? You can see that the graphs are plotted using the same scale, 14, let's say for the biomass, okay, for the cell growth, you can see it's very similar, isn't it? Like for example, this is the cell growth. So it looks very, very similar. Of course, it's not exactly similar, but you can see that the maximum, for example, the maximum concentration is about, how much? It's about 12. So this one is nearly 11 something, but yeah, it's about the same. Okay, so it means that my scale up is successful because of the similar performance. That is self. So how about the substrate consumption? The substrate consumption should be reducing because it means that it is consumed by the microbes. So my substrate is glycerol. Glycerol is the carbon source. So you can see that the same trend of the substrate consumption. Yeah. So it means that it's consistent in both platforms. And ultimate target is the product. So my product here is transaminase. Okay, it's not here. Yeah, so here is the profile of the activity of the transaminase that I got. Micro 24 is this one. Okay, and in the 7.5 liter is this one. This one. Okay, so the objective is to get about similar. So you can see that although it's not exactly similar, but the difference is minimum. So it means that it's very close. So this, that's enough to say that the whole fermentation performance is satisfying. It is reproducible from small scale to higher scale. Yeah, and another thing is when you analyze the data and you compare, so these are the results that I got, okay, in terms of the maximum cell concentration. What I got in Micro 24 is 11.3, 7.5 liter 11.7. And when I check using statistical analysis, you know about the significance or non-significance, we check the p-value. So if let's say the p-value is less than 0.05, it means that the difference is significant. I think this is statistics thing, right? So this is to show that the difference is not significant. Means that it's very close. 11.3 and 11.7 is quite close. And same goes to the rest of the parameters here. The specific growth rate, about the same. Transaminase activity, although there is a difference, but when I check using the statistical software, the difference is not significant. To say that, you know, like it's within a similar range. And same goes to the this one. Okay. So that is the last part. That is to analyze the fermentation performance between the two platforms. Okay, so that's all the steps that I did when I scale up, how I scale up the fermentation process from a small scale to a larger scale. And the same thing, if let's say you want, this is within the lab scale. If let's say you want to scale up from lab scale to pilot scale to industrial scale, you have to do the same thing, the same steps. I mean, first you have to characterize the scale up parameter. Yeah, this one is scale A because I use scale A. But if let's say you use other parameters like, for example, mixing time, you have to characterize the mixing time. Yeah? But basically, the steps, what I mean by this, the main steps, characterization, you have to analyze, you have to determine the conditions for the operating conditions, and then you have to run the fermentation in both scales at the same time, and then have to analyze the fermentation performance. That's the same. Yeah? Even though for the between the lab scale and pilot scale too, industry scale.
Alhamdulillah. Yan, simpan tu balik lah Jen.
Okay.
Keluarkan cuci
Right.
yang simpan.
Yeah. So that's what the CAS review is all about. Yeah. Just to show how to set up an actual Arabic fermentation from mini bioreactor to lab scale fermenter. So that's the end of today's lecture. We have covered actually what is scale up, what are the objectives of scale up, when do we need to do studies, what are the stages involved in scaling up studies, the changes in the operation, what are the methods in scaling up fermentation process, and finally we have a look at the case. Okay, any questions?
Oh,